All right, so new video for part 2 because it was kind of glitchy, so hopefully this will help. So anyway, 2 more examples and then one where we work backwards. Again, trying to hit all the different pieces and types of things that you'll see with these rational functions. This next one, if we take out a GCF from the numerator of 3x, that gives you x minus 1 left over. And then in the denominator, you factor like usual, just a typical trinomial. So x plus 4, x minus 3. So that means your domain is going to be x does not equal negative 4 and 3. Nothing cancels out. We don't need to reduce anything. So now let's go ahead and find the details. Remember that the x-intercepts come from the numerator equaling 0. So then if you do that, you get x equals 0 from this factor. The 3x gives you 0. The x minus 1 gives you 1. To find the y-intercept, you plug in x equals 0. That would give you 0 divided by negative 12, which is just going to be 0. The vertical asymptotes are going to be x equals negative 4 and positive 3, since nothing canceled out. And for horizontal or oblique, this is the third case that we have not touched on yet, but the degrees are the same in the numerator and denominator. When that happens, whenever they're equal, we have quadratic over quadratic, okay? You just take the leading coefficient divided by the leading coefficient, and that'll be your horizontal asymptote. So in this case, we're going to have y equals 3 over 1, right? We have a 3 and a 1 coefficient for the numerator and denominator, so y equals 3. So those are all the details. Put those points on the graph, label them. So we got 0 and 1 for our x and y intercepts. Vertical asymptote at x equals negative 4. Another vertical asymptote at x equals 3. We have a horizontal of y equals 3. Okay, so let's talk about this for a second. Whenever the horizontal asymptote is not equal to 0, so if this number here is anything higher than 0, especially when it's a quadratic over a quadratic, and for you guys, honestly, in this class, this is pretty much the only time you have to worry about this, is when you have a quadratic over a quadratic and nothing cancels. You want to check if the graph, so does the graph cross the horizontal asymptote, okay? It is possible to cross horizontal or oblique asymptotes. Those represent end behaviors. You will never cross through vertical asymptotes, but horizontal asymptotes, it's possible. Here's what we do. So we take the value of the horizontal asymptote, which is 3, and we set it equal to our function, 3x squared minus 3x divided by, and you know what, I'll use the original version, x squared plus x minus 12. All right, we want to solve this. If we actually solve this equation and we get an x value or 2, then we've just confirmed that there are a couple of points where it hits y equals 3. And so my first step would be to take the denominator and multiply that to both sides. Okay, so that'll essentially give us, on the left-hand side, 3x squared plus 3x minus 36. And on the right-hand side, since the denominator goes away, we just get the numerator, 3x squared minus 3x. Now, the 3x squareds cancel. You can add 3x to the left-hand side, which gives you 6x equal to 36 if you move the 36 over. If you divide both sides by 6, you get x equals 6. So we've just confirmed that when x equals 6, we have a point on y equals 3. So I'm going to put that on here as well. So 1, 2, 3, 4, 5, maybe about here somewhere, we have a point 6, 3 where the graph should go through. All right, so those are all the details. Now, the only things that would make sense to have here for our graph, I'm going to start with the middle since I know those points. And we have multiplicities of 1 for each x-intercept, okay? Those each have a multiplicity of 1, so we're just going to go through these points and then come back something like that. I mean, it's not perfect, but good enough. It's like a kind of lopsided parabola. Now, as far as what happens on the other parts of the graph, I need something, let me change colors here. I need something either up here or down here. And I also need something up here or down here. Those are the last two pieces. They got to go in one of those spots. Now, the only thing that makes sense on this side is up here. And the reason for that is because, first of all, we don't have any x-intercepts. If I did, I'd have a point here. So if I were to graph this, I would just create an x-intercept out of nowhere, which is bad. Okay, so that doesn't make any sense. It's got to be this first picture here in the top left corner. Second reason is the multiplicity of the asymptotes. So for this x equals -4 asymptote, notice the multiplicity is 1. Same with this asymptote. That means that we should see opposite behavior in the graphs. So if I'm going down, on one end, I have to be going the opposite way on the other. That always happens if the multiplicities are 1. Okay? If they were even, like a square, so if this x plus 4 was squared and the x minus 3 was squared, then they would be going the same direction, either both down or both up. Okay, and that's the same reason then, same logic that we're going to use over here, with the exception that, so we have to be going up on this side, and then when I get close to this asymptote, not only do I get close to it, I actually cross through it, and then I stay below it on the other side. Okay? So that's what the graph looks like. All right. That covers all the different horizontal versus oblique asymptote scenarios. The only thing we haven't talked about yet is what happens if something cancels out, which is where you get holes from. So I'm actually going to put in a spot here. We're going to label and figure out exactly where that hole is, but we're going to start exactly the same way as we usually do. We factor and cancel. So the numerator, if you do trial and error or split the middle or the AC method, whatever you want to call it, you should get 2x, x, and this will be a 2 and a 1. These will both be negative. So those are your factors for the numerator. By the way, if you're struggling factoring, again, we're going to be factoring a lot for this next assessment, so you want to make sure that you're comfortable with all the different techniques that we've studied for factoring, or rather we've reviewed for factoring this semester. Anyway, denominator is difference of squares, so that's x minus 2, x plus 2. Notice that the x minus 2 and the x minus 2 reduce, that cancels out, okay? And maybe backtrack. Before I do that, let's find the domain. The domain comes from the original denominators, so we're going to get x does not equal 2 and negative 2. Always want to find the domain before you reduce. That's exactly why there's a hole, and I'll show you in a minute. Anyway, the x minus 2's cancel out, so this does reduce to just 2x minus 1 over x plus 2. So that's our new function after it's reduced. And so we're going to use this to find all the details now. So the x-intercept, if you set that equal to 0, if you set the numerator equal to 0, you're going to get x equals 1/2. If you plug in 0 into the denominator, or I'm sorry, not into the denominator. If you plug in 0 into the x's, all that would be left is -1 divided by 2, which is -1/2. Vertical asymptotes come from the denominator. The only denominator that's left is x plus 2, so we get x equals -2. We have a horizontal asymptote. The degrees are the same, so we do leading coefficient over leading coefficient, and we get y equals 2. Now here's where this hole comes from, okay? So At the very beginning, we always find the domain based off the original equation. We know that x cannot equal, in addition to this vertical asymptote of -2, x equals, or x does not equal 2 is what we essentially kind of ignored for a second, right? Because we crossed those out and we eliminated those. So this came from the x minus 2 factor, okay? And we're going to use this value to find the whole, okay? To find the whole, you're just going to plug in x equals 2 into the reduced fraction, let's say reduced equation, to find the y-coordinate. So that's going to be 2 times 2 minus 1 over 2 plus 2. 4 minus 1 is 3. 2 plus 2 is 4. Okay, so we get a whole at 2 3/4. Okay? So essentially what that means is that's where the graph is currently at, but we skip over that value. Okay, so essentially when I graph this, label the intercepts. We got 1/2 for x, -1/2 for y, vertical asymptote at x equals -2, and then we have a horizontal at y equals 2. Well, hold on, backtrack. I just realized I put the vertical asymptote in the wrong spot. It should be on the left-hand side since it's -2. So x equals -2 is over here. There we go. And horizontal asymptote is y equals 2. With this whole at 2 3/4, so kind of estimate where that would be. I'd say maybe right around there. So there's my, actually probably a little lower. So there's my whole, okay? And now we fill in the graph. So on the right-hand side, I think it's pretty obvious that we have to have, let me try that again. I have to have something that looks kind of like this. And on the right-hand side, or sorry, the left-hand side, since the multiplicity of the denominator is odd, I know it's got to be opposite. So if it's down on one side, it'll be up on the other side and look something like this. Also, there's no x-intercept over on this side, so it cannot go through that. So it's got to be on top. Okay. I don't have to check, by the way, if it crosses y equals 2 for linear over linear, ever. And the reason is, I can just quickly show you. Let's pretend that it does. Maybe it crosses the horizontal asymptote like the previous example. So you're going to take 2, set that equal to your reduced equation. If you try solving for x, multiply the denominator to the left-hand side. You get 2x plus 4 equal to 2x minus 1. The 2x's cancel out when you subtract on both sides. And then you get this 4 equals -1, which makes no sense, which tells us that there is no x value where we go to y equals 2. Okay, so, and that will always happen with a linear by default. You'll never be able to get an x value for those. So just worry about anytime you have a quadratic over a quadratic and you should be good. All right, final example. This one's the easier ones. We're just working backwards based off the picture. We're going to create the function that produces this graph. So just as a visual, I'm going to plot and label the asymptotes they give us. So we have x equals -5. They gave you x equals 2 as well. And what's the other one? Y equals 2. So here's y equals 2. And I'm going to highlight a couple things so I can see some x-intercepts here. We got 5 and we got -2. And that's enough. That's all we need to write our equation. And so just working backwards, we're going to start with the numerator. The numerator tells us the x-intercepts. So look at the x-intercepts and work backwards. If we have -2 as an x-intercept, That means we got to see x plus 2 in the numerator. And in addition, notice just like in the previous unit, whenever it touches or bounces, okay, that's going to be a 2 exponent or a 2 multiplicity. Now the other x-intercept at x equals 5, that's just pretty standard. It goes through it. So it'll just be x minus 5 to the first. As far as your denominator is concerned, we use these, oops, that was poorly circled. We use the vertical asymptotes to get the denominator. We just work backwards, kind of like we use the denominators to get the vertical asymptotes, okay? If we have x minus 5, then x plus 5 should be a denominator factor, and if we have x equals 2, then x minus 2 should be another one. Also notice that for x equals 2, we have a down, down, right here, going the same direction on both sides of the asymptote. That means that that factor needs to be squared. Anytime we see that, it's going to be an even multiplicity, and we'll just go with the smallest possibility, which is 2. Now also notice that we have degree 3 in both the numerator and denominator. That means we should get a horizontal asymptote, which we have right here. It's y equals 2. So we know that we're supposed to take leading coefficient divided by leading coefficient to get 2. So it's really up to you, but probably the easiest thing to do would just be to put a 2 in the numerator. But anything that gives you 2 is fine, like 4 divided by 2, 2 divided by 1. Any of those scenarios would be fine. So this is your final answer here. All right, and that wraps up what you need to know for this tiny little unit.